Good evening, ladies and gentlemen. We're going to be talking about quite a few things tonight. We have electron configurations of ions to talk about. We're also going to be talking about electron affinity, metallic character, and some very important reactions that metals themselves have. And we're still dealing with the same chapter that deals with a lot of periodic trends, so we're going to talk about periodic trends. But let's talk first about electron configurations of ions here. And what we're going to do is when we create an ion and we're going to take electrons off of a neutral atom, we're going to remove those electrons from the highest principal quantum number that's in. And so let me give you an example of what we're talking about here. Let's say we take lithium in its neutral form and we write the electron configuration for lithium. It's going to be 1s2, 2s1, because lithium in a neutral form has 3 electrons. If we're going to remove one electron, which of course would be this electron right here is going to be removed. If we're going to remove that electron to form a lithium 1 plus ion, which is what lithium typically forms, we're going to take that electron out of the highest energy level. So we're going to be left with an electron configuration of 1s2 only, which will give that lithium ion 2 electrons, which now it has the same electron configuration as helium does. Another example that's really important to take a look at is, let's say we'll take a look at the electron configuration for a neutral atom of iron. Now I'm going to do this in noble gas configuration, so we're going to say we have argon, and then we have 4s2, and then we have 3d6. So looking at this really quickly here is our highest principal quantum number is going to be the 4s2. Even though we know that fills first before the 3d, it's still the highest principal quantum number, even though those two are very close together. So let's say we're going to make an iron 2 ion. So what we're going to need to do is we're going to need to remove electrons from the 4s, or the highest principal quantum number. So our new electron configuration is going to be argon 3d6, just like that. And we could do another one too if we wanted to, just to show you. Let's say we have the same thing. I'm going to write it up here. We have argon 4s2 3d6, but we want to form the iron 3 ion. The iron 3 ion. So what's going to happen is we're going to remove 3 electrons, and so for the first 2 are going to come off here, and then the remaining one comes up there, so we get 3d5 occurring just like that. And that's what happens when we remove electrons to form ions and writing those electron configurations. Now if we're going to add electrons to ions, again we're going to add the electrons to the highest principal quantum number. So let's say if we're going to add electrons, let's say we'll take a fluorine atom, and fluorine is going to have 1s2, 2s2, 2p5 electron configuration. So if we're going to add, we have to add to the highest principal quantum number, which is going to be the 2p. So we're going to get fluorine as in the fluoride ion, 1s2, 2s2, 2p6 now. It's now going to have a total of 10 electrons when you add 1 electron to it. So it's going to have an electron configuration of a noble gas. It does not make it a noble gas, it just has the electron configuration of a noble gas. And there we go. Next one, I'm going to have you try these at home, and we're going to have you try the calcium and the cobalt 3 ion and the chromium ion. So you try these. So what I would recommend you do is, why don't you pause this this video right now and try them out, and then hit play and see if you get the same thing. Okay, so try that out, pause them, and then hit play. Okay, so hopefully you paused them and hit play, and then now we're coming back and we're going to take a look at these. So we have calcium to start off with a calcium 2+, just like this. And what I'm going to do is I'm going to do noble gas electron configuration of argon, and well, that's it. It's just argon because it's lost 2 electrons and it's argon. Or we could write it all the way out and say 1s2, 2s2, 2p6, 3s2, 3p6, and we would be good. On the next one we have cobalt, and this one is in the 3+. And so what we're going to do here for cobalt is in period 4. So once again we're going to do argon 4s2, and then cobalt takes us out 1, 2, 3, 4, 5, 6, 7, 3d7 for our neutral atom. So to get us to electron configuration, we need to take off 3. So we're going to take off these there, and we'll just take off one there, and we'll call it argon 3d6. The next one is the chromium ion, and we were doing chromium 3, and so in its neutral form, chromium is once again going to be argon. Now this, remember, chromium is one of the anomalies and does a 4s1 3d5 in the neutral ion, so we're going to remove 3 electrons off of this guy, and I know we're moving 3 because we have a 3 plus charge, so the first one is going to be the 4s removed, take away that one, and then we're going to take away 2 of those, and so we'll call it 3d, we were 3d5, 4, 3, 3d3, so argon 3d3. And that's how we do electron configurations of just regular old ions plus those transition metals that sometimes have those d orbitals to deal with. Next thing we want to talk about is the idea of electron affinity. Now the affinity means a desire for, so these are going to be the energy change when an electron is added to an atom, measure of attraction an atom has to an electron. And so we have an example down here with a neutral chloride or neutral chlorine ion, and we're adding an electron to it to form the chloride ion, and you can see that we have a delta E, which is just energy, change in energy, and it's negative 349 kilojoules per mole, letting us know that this is an exothermic reaction. So when you do add an electron to chlorine, it does give off some heat. Okay. Now, a couple of the ideas that we need to keep in mind when we're dealing with electron affinity, and one is the more negative the value of an electron affinity is, the greater attraction an atom has for an electron. So the more negative a value is, not the more positive, because usually typically to remove an electron is a positive value, to gain an electron is a negative value. Positive values for electron affinity mean the atom doesn't want electrons. Now both of these are going to play into what our periodic trend is and kind of the reasoning behind our periodic trend for electron affinity. So if we were to draw the periodic table here, and that's a rough drawing of a periodic table, and we were dealing with electron affinity values, basically what happens is as you go down, electron affinity generally, but it's not really much of a trend. It gets less negative, or we could say more positive, meaning electrons up near the top of groups tend to desire electrons more. They have more affinity. And then as we go right across the periodic table, it tends to increase in negative value. So we'll say let's erase that, and let's probably say, which I think would be a better way to say it, would be it becomes more negative. And by being more negative, meaning you have more affinity. But the trick behind this is it stops at 7a, becoming negative. For the noble gases, these guys are going to have probably a greater than 0, and they do have a greater than 0 electron affinity, meaning they don't want electrons, and we know that because, hey, they're noble gases. They have a complete complement of their electrons. They have completely filled S and P sublevels, so they don't need electrons. Really, the greatest electron affinity is going to be right up here at the top, which is going to be fluorine. And basically, the reason why the fluorine has the greatest electron affinity is due to size. Fluorine is a relatively small atom, and so those electrons are close to the nucleus, close to that nuclear charge, that positive pull from those positive protons in the nucleus, and so any electrons that are around are going to get pulled in by fluorine, which is kind of what we talked about and what we read about in today's article that we read on hydrofluoric acid and how it's very electron demanding. It's looking for electrons. I'm going to kind of change gears a little bit and get out of affinity and talk about metallic character. And metallic character just describes what are the characteristics of metals, all that huge group to the left of the stair-step line on the periodic table. And we can say that there's a bunch of different characteristics metals have. They're shiny. They can conduct heat and electricity. We can smash on them with a hammer and flatten them out into a sheet. We can pull them out into a wire, and maybe have that wire conduct some electricity or whatever. Metals also tend to have low ionization energies. They tend to, and that's a typo right there, let me cross that P out, they tend to form positive ions, and we know that. Potassium forms a 1 plus, calcium forms a 2 plus. Anybody out there in the transition metals can form multiple charges for the most part. Fe2 plus, they're all forming positive ions, basically due to loss of electrons, that oxidation, and that happens. The trend, basically, on the periodic table, draw a periodic table, what trend do we have? So as we go down a family or group, the tend for metallic characters tend to increase, and as we go across, as you can expect, getting closer to those non-metals that are on that side of the periodic table, it tends to decrease the metallic character. So metallic character does tend to increase going down a periodic table. Now, what we're going to talk about now is we want to talk about some important reactions that are associated with these metals. And so I'm going to talk about basically 3 different types of reactions today. And I'm going to give you some examples of each one of these. And you'll need to know how to do these and how to apply them to any other reaction, essentially, or compounds. So the first one is, if we have a metal and we react it with a nonmetal, usually in a synthesis reaction or combination reaction, we're just going to form an ionic compound. And that should seem pretty straightforward to you. So let's say if we have some solid nickel and we react it with some oxygen gas. Basically what it's going to do is it's just going to form an ionic compound when we just take these two and put them together. So in this case, let's say this is nickel 2. So we'll have nickel 2 oxide formed. And we don't necessarily always know that nickel is going to form a 2 plus charge. We can look up some of those things, but nickel is going to have a 2 plus charge, oxygen is going to have a 2 minus charge, crisscross those charges, cancel them out, and now we get our nickel 2 oxide. And I don't think we are balanced here, so let's go ahead and balance, and we have 2 oxygen, so now we're balanced. Typically when we have a solid reacting with a gas, we typically form a solid, so it's going to be nickel 2 oxide solid. And that's a typical reaction for non-metal ionic compound, and this is just seen many times in combination reactions. Let's go to our next one here. This one's going to be a metal oxide plus a water yields a metal hydroxide. A metal oxide is just what it seems. Metal, it's a metal plus an oxygen all bound together. Water we know, and metal hydroxide was with the OHs. So give you an example of, let's say we have sodium oxide placed in water. What are we going to form? Well, sodium oxide is a metal oxide. Sodium forms a 1 plus charge. Oxygen forms a 2 minus charge. Crisscross those charges, and we get Na2O. And we're going to react this with water in a liquid form. And what we're going to do is we're going to form, as it tells us up here, a metal hydroxide. So the metal is going to be the sodium, and the hydroxide, well, it's a hydroxide. And if we're taking this stuff and we got water involved, we know this is a strong base. It's going to ionize, so this is going to be aqueous. So, and we could write the net ionic equation for this as well and break up the sodium and the hydroxide into ions, because net ionic equations are cool like that. Let's do another one. Let's say we have calcium oxide. Now calcium oxide is found in concrete, wet concrete before it dries, and oftentimes people that work with concrete worry about what gets produced, and we're going to find out what gets produced here real quickly. So let's say we have some calcium oxide, CaO solid, 2 plus charge on the calcium, 2 minus charge on the oxygen to CaO. I'm going to replace that with water liquid, and we are going to get calcium hydroxide. And I'm not breaking this up right now, even though I know it's a strong base, but if we were going to write a net ionic equation, we would definitely break these two ions up. And let's see, here we go. So The reason why people that work with concrete are often worried is because if you have calcium hydroxide and you get that on your skin, it can easily burn your skin, leave some chemical burns on there. So they often will carry with them maybe some vinegar, which is acetic acid, and they'll pour vinegar on their hands, which will counteract or neutralize the calcium hydroxide. Or they'll wear gloves, which is a smart thing to do anyway if you're working with concrete. Okay, the last one we're going to talk about is a metal oxide plus an acid, and it's going to form a salt plus a water, basically a double replacement reaction. So let's go back and take our nickel oxide, nickel 2 oxide solid, and we're going to react it. We'll react it with a strong acid, like in the form of hydrochloric acid this time. Now this guy's just going to act like a double replacement reaction. We're going to take the hydrogen and the nickel, and we're just going to have them switch places. And so we're going to form water. The hydrogen going with the oxygen. Remember, oxygen has a 2- charge. And we're also going to form a nickel chloride. Nickel chloride is going to be NiCl2. And if nickel chloride is in the presence of water, chlorides are soluble except for silver, mercury, and lead, and so this guy's soluble. We're going to write it as aqueous, just like that. And I don't think we're balanced there. 2 hydrogens, and now I have 2 hydrogens, 2 chlorines. There we go. So there's a nickel metal oxide plus acid yield salt and water. And that is it for tonight's lecture. You just need to take notes.